You know, every single time you send a text, stream a movie, or hop on a video call, you're tapping into this colossal invisible architecture that runs our world. So today, we're going to pull back that curtain and really dig into the fundamentals of digital communication. We're going to see how it all works, from a single click all the way to a global network.
It really all starts with a question that, let's be honest, feels kind of like magic, right? How does a simple click right here on your screen manage to travel across continents in literally the blink of an eye? Well, I'm here to tell you it's not magic, it's engineering. And we're about to break down exactly how it happens.
So, to really get how the digital world works, we have to start with the basics. What even is communication? Because, whether you're shouting across a parking lot to a friend or sending an email to someone on the other side of the planet, the fundamental goal is always the same. Okay, so here's the textbook definition. But the key here isn't just sending something. The real goal is to make sure the other end receives a faithful, or as it says here, an acceptable replica of what you sent. That one little word, acceptable, is everything. It's the difference between a crystal clear phone call and just a garbled, useless mess of static. So how do you actually build a system that can do that? Well, it turns out that pretty much every communication system you can think of, from an ancient smoke signal to the entire global internet, is built from the exact same 5 basic building blocks, kind of like Lego. Let's take a look at what they are. And here they are: the source, the transmitter, the transmission system, the receiver, and the destination. Seriously, just 5 parts. Think of this as the universal recipe for sending any message anywhere. Let's see how they work together with let's say, a delicious example. First up, we have the source. This is where the whole idea begins. So let's imagine you decide you're hungry and you want to order a pizza. In this case, your hungry brain, you are the source. You're generating the message, I want a large pepperoni pizza. Next, you need a transmitter. See, that idea in your head isn't a sound wave just yet. Your voice box and your mouth, they act as the transmitter. They take that thought and transform it into acoustic energy, actual sound waves that can travel through the air and into your phone. Now, the transmission system. This is the physical path the message actually takes. It could be a phone line, a fiber optic cable, or radio waves from a cell tower. And this is also where things can get a little messy. Think of it like static on the line or a bad cell signal. This system can introduce noise or distortion that messes with your message. So on the other end, at the pizza shop, you've got the receiver. Its job is to grab that incoming signal, do its best to filter out all that static from the line, and convert those sound waves back into a message that someone can actually understand. And finally, the destination. This is the employee at the pizza place who hears and understands your order. The original message, large pepperoni pizza, has been successfully recreated. The system worked. Pizza's on the way.
Okay, so that's the universal model for everything. But now let's see what happens when we apply this blueprint to our world, the digital world of computers, where we're not just sending simple sounds, we're sending complex, structured data.
This brings us to what we call data communication. What makes this different is that it's not just about physical wires and connections anymore. No, it's this intricate dance between the hardware that you can actually touch and the software you can't, all the programs and instructions that manage the entire exchange.
Now, for data communication to actually work well, 4 things are absolutely crucial. Delivery and accuracy, those are kind of obvious, right? The data has to get to the right place, and it has to be correct when it gets there. But timeliness and jitter, these are the unsung heroes of things like video calls. You need those little packets of data to arrive on time and, just as important, at a consistent, steady pace. Otherwise, you get that choppy, frozen screen look we all hate.
Okay, so you've got 2 devices physically connected. But how do they actually talk to each other without it just being total chaos? Well, they need to agree on a shared set of rules. They need what's called a protocol.
A protocol, really, is just an agreement. Without it, 2 devices can be plugged into each other, but they can't actually communicate. It's like having 2 people in the same room, but one only speaks Swahili and the other only speaks Portuguese. They can hear each other making noise, but no real information is being exchanged. It's just gibberish.
So what are these rules about? Well, a protocol usually governs 3 main things. You can think of syntax as the grammar of the language, semantics is the vocabulary, what do the bits and bytes actually mean, and timing is the rhythm of the conversation, making sure both devices are speaking and listening at a compatible speed.
Communication isn't always a 2-way conversation. Sometimes it's simplex mode, which is a one-way street, like your keyboard sending commands to your computer. Then there's half duplex, where both sides can talk, but they have to take turns. It's just like using a walkie-talkie where you have to say over to let the other person know it's their turn.
And then we get to the mode we're all most used to in our daily lives, full duplex. This is a natural, two-way conversation where both sides can talk and listen at the exact same time. A normal telephone call is a perfect example of full duplex communication in action.
All right, so we've figured out how two devices can talk to each other, but how do we scale that up? How do we connect millions or even billions of them all together? Well, that's when we start to build a network.
At the most basic level, networks are built on two types of connections. You have point-to-point, which is like having a private, dedicated phone line just between you and one other person. And then you have multi-point, which is more like a party line, where a whole bunch of devices share the same connection. This core idea of sharing resources is really the foundation of all modern networking.
So what makes a network a good network? Well, it's usually judged on three key things. First, performance. Is it fast and responsive? Second, reliability. How often does it fail? And more importantly, how quickly does it recover when it does? And of course, security. Is your data actually safe from prying eyes?
When we talk about performance, one of the most important things we measure is called throughput. The easiest way to think about this is just the width of the data pipe. A higher throughput means you have a wider pipe, which lets more bits of information, more of your video stream, more of your file download flow through every single second.
And that brings us right back to where we started. This quote says it all. A network is a communication system, albeit a very complicated one. The internet, in all of its mind-boggling complexity, is still, at its heart, just a communication system. It's built on those same 5 Lego blocks we started with, just scaled up to a global, unbelievable level.
So there you have it. You now know the fundamental recipe, the blueprint behind every message, every video stream, every single connection you make. The blueprint itself is surprisingly simple, but the possibilities it unlocks, they're basically infinite. So the real question is, what will you build with it?